So we can get delta H for a reaction using Hess's law, like we just did. Or we can also get it from what are called standard enthalpies of formation. Delta H is the change in enthalpy, and so we can call 0 whatever is convenient. We measure changes in altitude relative to sea level, right? Because the center of the Earth as 0 is not convenient, but sea level is very convenient. So we chose that to be 0 elevation. We measure changes in enthalpy relative to the enthalpies of pure elements in their standard states. We decided that, okay, we'll call our baseline, our 0, the elements in their regular forms. And then we'll look at how a reaction changes from that. Well, what are those standard states? It's a defined set of conditions. If you have a gas, it will be the pure gas at 1 atmosphere of pressure. If you have a liquid or a solid, it will be the pure substance in its most stable form at 1 atmosphere of pressure and the temperature of interest. Usually that's going to be 25 degrees Celsius, room temperature. If you have a substance that's in solution, then it's a concentration of 1 mole per liter. So those are the standard states. A standard enthalpy change is the enthalpy change when all the reactants and products are in their standard states. And we put this degree sign up there to indicate standard. Standard enthalpy of formation, now we're adding a subscript F. That's the enthalpy change for the reaction forming 1 mole of a pure compound from its constituent elements. The elements have to be in their standard states, and we're making 1 mole of product. For a pure element in its standard state, the heat of formation is 0, because we defined it that way. Okay? How do you know what those standard heats of formation are? You look them up. So for an element in its standard state, like here's bromine. So there's bromine atoms in the gas state. That's not how they normally are. Bromine is normally found as a diatomic molecule, and it's a liquid at room temperature. These are at 298 Kelvin, which is 25 degrees Celsius. This is the most stable form of bromine at room temperature. So that has a heat of formation of 0. Here's calcium. Calcium is a metal. This is its most stable state, 0. When you have it calcium oxide, calcium carbonate, then the enthalpy change or the heat of formation is different. Here's another example of 2 different states of carbon. Carbon in the graphite is considered the standard state, that's 0. Carbon in the diamond form is plus 1.88. So we look things up over here, okay? The standard enthalpy of formation, also called the standard heat of formation, we tend to substitute heat in for enthalpy. The standard enthalpy of formation for elements is 0. That's like being at sea level. We've just decided that's what we're going to call 0. For most compounds, the standard heat of formation is going to be negative, because when you make a compound, it typically releases energy. So that's just like going below sea level. So the standard enthalpy of formation for methane, we can look it up in the table, is minus 74.6 kilojoules per mole. And we write a reaction for this where we're starting with the elements that compose CH4 in their standard states. So we've got carbon and hydrogen, so we need carbon in its standard state. That's the most stable form right there, carbon. And hydrogen, its most stable form is H2. And so we need 2 of these, and we'll make the CH4. This is not necessarily representing how that substance is made, but we can describe it this way. So this is a formation reaction for methane. We're combining the elements in their standard state to make 1 mole of the compound. If you're not sure which the standard state is, when you look in the table, just find the one that has a heat of formation of 0, and those are the ones you should use. Sometimes we end up with coefficients here that are fractions, because the way this is set up, we have to make 1 mole of compound. Let's look at writing the formation reaction for carbon monoxide. So we're looking at making carbon monoxide from the elements in their standard states. Well, here's the two elements, carbon and oxygen. We have to figure out what the standard states are. Well, there's several different states for solid carbon. The one that has delta H0 is graphite. So that's what we're going to put here, graphite. And for oxygen, its standard state is O2. So we need these in their standard states. We're not done yet because this isn't balanced, is it? We're going to balance the equation, but we have to end up with the coefficient on CO being 1. So if we just come back here and balance it over here, normally how would we balance this reaction? Well, we'd put a 2 over here, right, because we've got 2 oxygens, and we need 2 oxygens over there. We've got 2 carbons there, and so we're going to put 2 carbons over here. That's how we would normally balance it. For formation reactions, the coefficient over here has to be 1. So I'm going to divide all the coefficients by 2. So that's 1. This was an understood 1. I'm dividing by 2, and this is divided by 2. And that's how we end up with this. 1 carbon, half a molecule of oxygen will make 1 molecule of CO. The heat of formation here, you look it up. It's found in a table. The table would be given to you on an exam. Any questions? This isn't confusing at all. Okay. Write equations for the formation of sodium chloride and lead nitrate from the elements in their standard states. Include the values of the heat of formation for each equation. Okay, so for the first one, we're looking at sodium chloride, right? What are the 2 elements? Sodium and chlorine, right? So those are the 2 elements. I'm going to leave a lot of space around them because I'm going to have to write other stuff. And I'm trying to make NaCl solid. Well, what's the standard state for sodium? It's a solid. For metals, it's going to be a solid, and metals are always atomic elements, so it's just Na. What about Cl? That's one of those diatomic molecules, right? So we can pretty much guess that that's going to be Cl2, and from the color coding on the periodic table at room temperature, what's its state going to be? A gas. So we can kind of figure that out. We can also look at the table. So this is table 6.5. Chlorine. So there's chlorine atoms. That's not 0. Chlorine, Cl2 in the gas state. This is the standard form. So that's the one we want to use. While we're here, let's look up the heat of formation for sodium chloride because we need that number. So here's sodium chloride solid. That's the one we're writing the equation for. Minus 411.2 kilojoules per mole. Minus 411.2. So delta HF is going to equal minus 411.2 kilojoules. So we've got our standard states, but this isn't balanced. We want to keep this as a 1. I've got 1 sodium and 1 sodium, so that's okay. Here I only need 1 chlorine, but these are coming in pairs. So I need half of that. So you can do it that way using fractions right off the bat, or you could balance it without using fractions and then divide everything by whatever coefficient you get here, like I did with the carbon monoxide equation. Any questions about that one? Stunned silence. So now we're going to do lead nitrate. Well, what are the elements in there? There's lead and nitrogen and oxygen. We need to identify the standard states of those. So we can take a pretty good guess at these. Lead is a metal, so it's probably Pb solid. What about N? It's diatomic, so it's going to be N2 and it's going to be a gas. And same thing for oxygen. Let's double check. Oh yeah, lead's not on this one. That's so stupid. Nitrogen is, though. Where'd you go? Here it is. So nitrogen, we were right. N2 gas, and oxygen, O2 gas. Lead's not on there. What do we do? Well, oh, that's not what I wanted to do. Well, we're going to have to look that up. I'm going to write delta HF0 over here, but we can't look it up on that table. There's another table. Let's balance this before we go on to that. I need one lead atom. I've got one over there. How many nitrogens are in this? 2 nitrogens, right? So there's my N2. And how many oxygens? 6. So if I put a 3 in front of the O2, it's all good. We have to find the heat of formation. There we go. So this is an appendix in your book. So it's got more stuff over here. So here's lead. And lead in its solid state is the one with the 0. Now you got to be careful here because this has some other information. We've got the standard heat of formation, and we also have those other weird things that we'll talk about later. But here we can look up lead nitrate, and it's minus 451.9. So minus 451.9 kilojoules. Any questions? We're just going to finish this section. So we can use these to calculate the standard heat of reaction. The heat of formation that we can look up corresponds to the formation of a compound from the elements in its standard states. The negative of that represents the decomposition into the elements in their standard states. And so one way to calculate the heat of formation is to take the reactants and pretend we're dropping them down to elements in their standard states and then forming the products from those elements. So what we can do is we can say that the heat of formation for a reaction is we take the heats of formation of the products. So we're making the products from the elements in their standard states. So we look up the heat of formation for each of the products. We multiply by whatever coefficient is in the balanced chemical equation. Then we're going to subtract the heats of formation from the reactants because we're saying, well, that was the amount of energy needed to make that. What about the energy change when we take it apart? And so it's negative, and that also needs to be multiplied by the coefficient of the reaction. So here's this reaction. We've got methane reacting with oxygen to form carbon dioxide and water, burning methane basically. So what we're thinking about when we do this is we take these reactants and we're going to take the CH4 apart into carbon and hydrogen, and the oxygen's okay because it's already in its standard state. So we can find this amount of energy because the heat of formation for methane is minus 74.6. So if I decompose it, if I run this backwards, it's going to release 74.6. And then I'm going to imagine, well, now I've got all the elements. I'm going to make CO2 from those, and I'm also going to make water from the standard states. So I can look up making CO2 and find out that this is delta H. And I can find out the energy change from making water, and it's this one down under the pointer. Can't remember what's on the next slide. No, I don't want to do that. So to calculate the standard heat of reaction for this, I'm going to take the heats of reaction for the products, CO2 and H2O. So for CO2, it's minus 393.5. And for H2O, it's minus 241.8. But there's two of those. So this has to be multiplied by 2. So that's what I get when those are made. Negative 393.5 plus 2 times negative 241.8. That is the sum of the products. Then I need to subtract the heats of formation of the reactants. So I'm subtracting, here this was adding together, I'm subtracting the sum of the reactants. So this is minus 74.6. So I take my minus 877.1 and I subtract negative 74.6. And I'm going to get minus 802.5 kilojoules. So that is the standard heat of formation for that reaction as written. And I'm sure that was just super clear and you're just all ready and raring to go to solve these problems. Not a chance. Any questions? Right. We're going to stop there.